I'll begin this lesson with the very first mathematical magic trick that I ever learned. I want you to think of any number from 1 to 10. Got it? Double that number. Now, with the number you're thinking of now, add 10 to that number. Now divide by 2. And finally, subtract the number that you started with. Concentrate. I believe you are now thinking of the number 5, right? In my first trick, I began by asking you to think of any number between 1 and 10. In fact, you could have thought of any number at all. It could have been a small number, a big number, a negative number, even a fraction. In fact, if I were asked to teach a class in algebra, I would probably start by doing this magic trick, since it illustrates the power of abstract thinking. Now, I don't know your original number, so let's call it n, as in number. By the way, this is probably the single most important idea in algebra, which is the notion of letting an unknown quantity be represented by a letter, which is called a variable. Here, the variable is n. Then, what did I ask you to do? Double the original number. So now you're thinking of the number 2n. Next, we add 10, giving us 2n plus 10. Then I asked you to divide by 2. So when we cut both terms in half, we get n plus 5. Finally, I asked you and everyone else to subtract the number they started with. And what number did everyone start with? N. So when we subtract n, we get n plus 5 minus n, which is 5, as predicted. The next few tricks that I'll show you are all based on very simple algebra, like the trick we just learned. But they'll still fool and impress most people. Okay, for this next trick, I'll ask you to go get a deck of 52 cards, so make sure you've taken out any jokers and you have 52 cards. Now shuffle those cards if you'd like, and deal 30 cards on the table, exactly 30. Go ahead and pause the video, I'll wait. Okay, now that you have 30 cards on the table, I want you to count the number of black cards in your pile. There could be 15, there could be more, there could be less. I certainly can't be sure. Now, look at the other pile and count the number of red cards. Again, I have no control over how many red cards are in that pile. So now I want you to take those two numbers and subtract them. Okay, so the number of black cards in the first pile minus the number of red cards in the second pile. All right, I'm going to try and figure out the answer to the subtraction problem using a little bit of forethought. I thought so. It's 4, right? Good. For the black and red trick, you begin by dealing 30 cards on the table. I truly don't know how many black cards are in that pile. Let's call that number B. Now, if there are B black cards in that pile, then how many red cards are in that same pile? Well, there are 30 minus B red cards in that pile. Now consider the other pile of cards. How many red cards will it contain? Well, there are a total of 26 red cards between the two piles, and the first pile has 30 minus B of them. So the second pile must have how many? Well, 26 minus the 30 minus B red cards from the first pile gives us B minus 4. Aha! So even though I don't know how many black cards or red cards that you have in either pile, I do know that when you take the number of black cards in pile 1 and subtract the number of red cards in pile 2, you are guaranteed to get B minus the quantity B minus 4, and that always equals 4. Let's hear it for algebra. Let's try a similar experiment, but to make it harder, I'll ask you to deal 3 piles of cards. By the way, you could use any objects. They could be coins, paper clips, or whatever, but I'll use cards. And so I'm going to ask you to deal 1 card in each of the 3 piles. Then another card in each of the 3 piles. And keep dealing 1 card into each pile until you're satisfied. Okay? My only condition is that each pile has the same number of cards, and you should have at least 3 cards in each pile. Okay? So you should now have 3 piles of cards in front of you, a left pile, a right pile, and a middle pile. All right, now take 3 cards from your left pile and put them in the middle pile. Here, I'll do that here. 1, 2, 3. All right, take 3 cards from your right pile and place them into the middle pile. 1, 2, 3. All right, now count the number of cards in your left pile. I have 2 cards left in my left pile. And remove that number of cards from the middle pile, say 1, 2, and place them on the right pile, like so. Now take a card from the left pile or the right pile, up to you, and place it in the middle pile. All right, finally, count the number of cards that you have in the middle pile. Now, I have no idea how many cards you started with, but I'm going to predict that at this point, your middle pile has exactly 10 cards. How did I do? Good. Before I explain the secret to the trick with the 3 piles of cards, you might want to pause the video and see if you can work out the algebra yourself. Okay, here it is. The trick begins with every pile having the same number of cards. How many cards does each pile have? By now you know the answer. It's n, of course. So we have n in this pile, n in that pile, and n in that pile. Then you were asked to take 3 cards from the left pile and 3 cards from the right pile and place them in your middle pile. Now your situation looks like this, where the left and right pile each have n minus 3 cards, right? They each lost 3 cards, and the middle pile has 6 more, so it has n plus 6 cards. Next, you're asked to count the cards on the left pile. Then remove that many cards from the middle pile and place those on the right pile. All right, that's a brainful. When we remove the n minus 3 cards from the middle pile and place them on top of the n minus 3 cards on the right pile, then the right pile now has 2n minus 6 cards. But that's not so important. Here's the surprising part. How many cards are now in the middle pile? Well, we had n plus 6 cards, and we just lost n minus 3 cards. So when we do n plus 6 minus n minus 3, we get exactly 9 cards. Finally, when we add 1 more card to the middle pile, doesn't matter which pile it came from, that middle pile is guaranteed to have exactly 10 cards as predicted. For this next trick, we'll use some larger numbers, so you may want to use a calculator, but if you prefer to do it on paper, that's fine too. To begin with, I want you to think of a 3-digit number where all the numbers are different and in decreasing order, so they go down. For example, you could think of 3, 2, 1, or spread them out, 8, 5, 2, or 9, 7, 0, whatever you'd like. Go ahead and write that number down or enter it on your calculator. Now, reverse the digits of your number, which will give you a smaller number. For instance, if I chose 970, then its reversal will be 079. Okay? Now, subtract the smaller number from the larger one. For example, I would do 970 minus 079, giving me 891. Okay? Have you done the subtraction? Good. You now have a number that even you didn't know you'd be thinking about. All right. Now take this number, whatever you have, write it backwards, and add those two numbers together. For example, if you had the number 365, you would reverse it to get 563, and then add those numbers together to give you 928. Okay? So you should now have as a total either a 3-digit or 4-digit answer. Concentrate on that number. I'm getting the distinct impression that it's a 4-digit number, beginning with 1, then 0, then 8, then 9. Is your number 1089? I thought so. The algebra behind the 1089 trick is just a little bit more complicated than the previous tricks, but we can do it. Originally, you chose a 3-digit number, which we'll call ABC, where A is the largest digit and C is the smallest digit. Remember, they went in decreasing order. Notice that A also represents the hundreds digit, B represents the tens digit, and C is the ones digit. The number ABC really is the number 100A plus 10B plus C. Next, we reverse the number to get CBA, which really is 100C plus 10B plus A. When we subtract this from the first number, we get, well, let's see. We notice that the 10B's cancel, and we're left with 99A minus 99C. That's a multiple of 99. It's 99 times A minus C. In other words, after we do our first subtraction, the answer has to be one of these multiples of 99. When we add any of these numbers to its reversal, we always get 1089. We can verify this with algebra, but it's easier just to verify the 4 possible situations. Thus, no matter what number you have at this step, when you add its reversal, you're guaranteed to end up with 1089. My next trick uses one of the most fascinating numbers in mathematics. Probably the most famous number is the number pi, 3.141592, and so on. But that's not the one I'll be using. Instead, I'd like to talk about the number phi. Phi, which begins 1.618033, is often referred to as the golden ratio, and has many beautiful mathematical properties. For example, let's take a rectangle with dimensions 1 by phi, so its width is about 1.6 times as long as the height. Next, take a 1 by 1 square from one end of the rectangle and remove it. The new rectangle has a height of 1 and a width of about 0.618. which turns out to be the same proportions as the original rectangle. Notice that when we turn the rectangle on its side, it's still the case that the width is about 1.6 times as long as the height. You can use this relationship to find an exact formula for phi. Namely, phi is equal to 1 plus the square root of 5, all that divided by 2. And that gives us the 1.618. Phi has been deliberately used by artists, architects, and advertisers to produce appealing designs. Even Leonardo da Vinci used phi in some of his work. It's been suggested that the most aesthetically pleasing rectangle to look at has golden proportions of approximately 1 by 1.618. Phi is also intimately connected with the Fibonacci numbers, which, as we know, start with 1 and 1, and then every number is the sum of the two numbers before it. So look here, you see in our list we have 3 plus 5 is 8, then 5 plus 8 is 13, and so on. Now, if you look at the ratio of consecutive Fibonacci numbers, we see that their ratios actually get closer and closer to 1.618. And as we get farther and farther out, these ratios get closer and closer to phi. By the way, I and other mathematicians sometimes pronounce this number phi instead of phi, especially to remind us of its intimate connection with the Fibonacci numbers. Phi is also referred to as nature's number, since, along with the Fibonacci numbers, they seem to show up everywhere. The number of petals on a flower, or the number of spirals on a sunflower or pine cone or pineapple, often turns out to be a Fibonacci number. Some have suggested that many proportions in the human body, including the ratio of a person's height compared to the height of their belly button, is often close to the golden ratio. Although I have not personally conducted this research, I'm a little bit skeptical about that one. Nevertheless, it's certainly the case that phi appears everywhere, in mathematics, art, and nature, and as I'd like to now demonstrate, in magic too. Behold the digits of phi, truly one of the most magical numbers in mathematics. I'm going to show you something I think is pretty amazing about the number phi. With me are Leslie and Andrew and Tammy and Art, and they're going to help me in this experiment. Let's see, so I'll give Art, I'll give you these cards. Here, Tammy, you can have these. Here, have a 6 as well. Leslie, why don't you take those? And Andrew, I'll give you the rest of these, and I'll save the decimal point for later. So mix up your cards. Take your cards, mix them up, and when you're satisfied, place them down in a pile. What I'm going to do is I'm going to create 4 4-digit numbers. And Andrew, I'm going to ask you to add up these 4-digit numbers as they are created. Okay, so our first number here is 3874. Our second number is 3149. Our third number is 0188. And our last number is 8, 9, 6, and 9. Okay. So when you add those numbers together, you should probably get a 5-digit number. What number do you have?
I have 16,180.
16,180. Here was my prediction. 16,180. And by the way, I said I'd use this decimal point later. If we stick it right there at the beginning, we get 1.6180. Like I told you at the beginning, phi is everywhere. For the phi trick, how could I be so sure that the final total would be 16,180? I began by taking the first 16 digits of phi, and let's call my assistants A, B, C, and D. I give the last four digits, 9894, to D. The last three digits, along with the number 6, go to C. Those would be the numbers 6874. The middle digits, 8033, go to A, and the remaining digits, 1198, will go to B. Notice that when we create the four-digit numbers, A always provides the first digit. B provides the second digit, and so on. So our four numbers will have to look like this, where the first column contains the digits 8033 in some order. The second column has 1198 in some order, and so on. If you look what we did earlier, you'd see that. So the final numbers are going to have to look something like this. So the last column of numbers, no matter what their order is, because they all came from D, are going to have to add to 30. So the total is guaranteed, right? Because I have what? A 9, an 8, a 9, and a 4. That total is guaranteed to add to 30. It's going to end in 0. If you write down the 0 and carry the 3, what do we see about the next column? Well, it has to add, with the carried 3, it's going to have to add to 28. Write down the 8 and carry the 2, the next column will add to 21. Put down the 1, carry the 2, and finally the first column, along with that carried 2, along with the 8033, will add to 16, producing our predicted total of 16,180. And when we throw in the decimal point, just for fun, we're guaranteed to get 1.6180, which are the first 5 digits of phi. As it turns out, there was nothing particularly special about the number phi here. Once you give your 4 volunteers any group of numbers, you know what their final total will be, regardless of how each individual arranges their cards. I just thought it was cool that the first 16 digits of phi could be chosen in such a way as to partially replicate itself. But as we'll see in the next trick, the number phi actually plays a more meaningful role. Our next trick is inspired by the Fibonacci numbers. Andrew, I'm going to give you a chance to create your own Fibonacci-like numbers. So start by giving me any number between 1 and 20, and I'll write it here.
17.
17. And another number between 1 and 20. 8. 8. Okay, so continuing like the Fibonacci numbers, we see 17 plus 8 is 25, and 8 plus 25 is 33, and I'm going to keep on going like that. But Andrew, what I want you to do is, as I write all of these numbers down, I want you to add them on the calculator until we get all 10 numbers, okay? So while he's doing that, 25 plus 33 is 58. 58 plus 33 is 91. 91 plus 58 is 149. By the way, I think the total is going to be 1,649, but I'm getting ahead of myself. Maybe 1,639. Carried the extra 1 there. Okay, keep going. I get 240, 389, and finally 629. Andrew, when you add up all those numbers, what do you get?
I get 1,639.
As predicted. But the real point of this trick is, before I started, I wrote a prediction on the back of this sheet. And that prediction says that, this is the last calculation. I want you to take the 10th number. I couldn't have known what 2 numbers you'd give me. I certainly didn't know what 2 numbers I'd end with. I want you to take that 10th number, 629, divide it by the 9th number, 389, and give me the first 3 digits of the answer.
1.61.
1.61. Like I told you, the golden ratio is everywhere. I call this trick the Fibonacci sum trick because the numbers are created like the Fibonacci numbers, 1, 1, 2, 3, 5, 8, and so on. Now, I don't know what numbers you started with, so let's call them x and y. Thus, the number in row 3 will be x plus y. Now, row 4, well, that's the sum of rows 2 and 3. So when we add y to x plus y, we get x plus 2y. Continuing this way, the rest of the rows will have 2x plus 3y, 3x plus 5y, 5x plus 8y, 8x plus 13y, 13x plus 21y, and finally 21x plus 34y. By the way, it's no coincidence that all those coefficients are Fibonacci numbers, but I digress. Now let me first explain how I found the sum of those 10 numbers so quickly. If we add all 10 of those numbers together, we get a grand total of 55x plus 88y. Now what makes that number so special? Well, 55x plus 88y, we can factor out an 11, and that's 11 times the quantity 5x plus 8y. But notice, 5x plus 8y is actually row number 7. Row 7 contains 5x plus 8y. So the way to add all those numbers quickly is as soon as I see the number in row 7, I just multiply it by 11. Okay, so for example, if the number in row 7 is 81, then the grand total is 891. Now I'll show you a quick way to multiply by 11 in the next lesson. Okay, so how can we guarantee that the final ratio of row 10 divided by row 9 would start 1.61? The secret has to do with a surprising property of fractions that they don't teach us in school. Now, the short answer is you'll always get 1.61 as that final ratio. No matter what two positive numbers they start with, we're guaranteed to get 1.61. What I'm going to show you now is why we always get 1.61. Now, when we first learn about fractions, we're taught that to add two fractions, like 1/2 plus 1/3, we add them by putting them over a common denominator. Here we have 3/6 plus 2/6, which is 5/6. But what happens? What happens if you take two fractions and you add the numerators together and add the denominators together? This has a special name in mathematics called the mediant. It's the word median with a T at the end. For example, the mediant of 1/2 and 1/3 is, well, the numerator is 1 plus 1. The denominator is 2 plus 3. So we get 2 over 5. Now, the mediant has the interesting property that it always lies in between the original two fractions. For example, the fractions 1/3 and 1/2, their mediant 2/5 lies between them, right? 2/5 is between 1/3 and 1/2. And you could verify that because 1/3 is 0.333 something, 2/5 is 0.4, and 1/2 is 0.5. In general, for any positive numbers a, b, c, and d, if the fraction a over b is less than the fraction c over d, then the mediant, which is a plus c over b plus d, will always lie between them. I'll leave the reason for this as an algebra exercise, but let's see how this applies to our magic trick. When we divide row 10 by row 9, we're looking at the quotient 21x plus 34y divided by 13x plus 21y. But that's the mediant of the fractions 21x over 13x and 34y over 21y, so it has to lie between them. But 21x over 13x, that's just the fraction 21/13, and it begins 1.615. And 34y over 21y, well, that's the fraction 34 over 21, and that begins 1.619. So the ratio, 21x plus 34y over 13x plus 21y, the median of those two numbers, has to lie between 1.615 and 1.619. That's why I was so sure that the first three digits of the quotient must begin with 1.61. As should come as no surprise, if you continue this leapfrogging process of creating more and more numbers in Fibonacci fashion, the ratio will get closer and closer to the golden ratio, 1.618. For my last trick, bring out a calculator. Okay, now I want you to think of a 4-digit number that you're going to remember. Perhaps it's your PIN number or the last 4 digits of your credit card. Got it? Okay. Now enter that PIN number on a calculator, and for extra security, enter it twice so you have an 8-digit number. So if your PIN was 1234, which I would not recommend, by the way, then you would enter 1234, 1234. Got it? Remember it. Don't forget your 4-digit PIN. Okay, now as you'll soon learn, one of my favorite numbers is 9. So take that 8-digit number and divide it by 9. Now whatever answer you have, divide that number by 9 again. Got it? And now for extra security, divide that number by your original 4-digit PIN. Okay? You probably have some big number with lots of decimals, but let me see if I can get it. Concentrate on your answer. I have some digits here in front of me to help me concentrate. It feels like you're just counting. 1, 2, 3, 4. That doesn't make sense. Oh, wait. I got it. Bring out this decimal. 6 and 9. Do you have 123.469? Is that right? Maybe you should get a new PIN number. Hey, by the way, if you want to know my PIN number, it's the last 4 digits of pi. The secret behind this trick is pretty simple, yet it usually gets a very big reaction. It's based on the fact that if you take any 4-digit number, let's say your PIN number was 2358, and if you write it twice so it appears as an 8-digit number like 2358, 2358, well, that's just the same as the original 4-digit PIN multiplied by 10,001. Right? Check it out. If you took 2358 times 10,001, you would get 2358, 2358. So it should come as no surprise that when you divide this by the original 4-digit PIN number, you're guaranteed to get back 10,001. And if you divide this number by 9 and then by 9 again, your answer begins 123.469. What makes this trick so deceptive is that we divide the 8-digit number in the opposite order. First we divide by 9, then 9 again, and then by the 4-digit PIN. But either way, we're guaranteed to get 123.469.